Okay, discrete optimization, mixed integer programming, branch and cut second lecture. Okay, so this is the real stuff now. Okay, so one of the things that we saw in the last lecture is that we can generate these polyhedral cuts. Okay, but one of the things that we did was basically adding them all inside the the formulation at the beginning. That's not exactly how branch and cut works. So what I want to do now is take this concept and then tell you really what a branch and cut algorithm is doing. Okay, so we're going to see two things: cover cuts. Okay, and you'll see why we'll talk about them. They're very very frequent in mixed integer programs, and then we'll move to the TSP, which is probably the biggest success stories of optimization. We can solve really large TSP optimally at this point. Okay, so cover cuts first. Okay, so cover cuts, we are looking at constraints which are inequalities, okay, linear inequalities, a sum of coefficients and variables which have to be smaller than b. Okay, right, the simplest kind of stuff that you find all the time inside your MIP. Okay, so a sum, coefficient ai, aj, multiplied by a binary variable xj, 0, 1, has to be smaller than b. Okay, so can we find facets for these constraints? Okay, can we find facets of the polyhedra which are derived from these constraints? Okay, and the key concept here, the title is cover cut, right, is the concept of cover. And essentially what you need to think about is a cover is going to be a set of variables. If you set them all to 1, you're going to violate the constraints. Okay, it's basically telling you these variables, not all of them can be 1. Okay, and so basically, what you do is you look at a subset of these variables. Okay, you look at the coefficients, and if you sum all these coefficients, they are greater than b. And therefore, you know that if you select all these variables, put them to 1, you're going to violate the constraints. Okay, so that's the concept of cover. Basically, these variables cannot be selected all at the same time. Okay, and so a cover is going to be minimal. Okay, so that's the opposite of a maximum click. Right, it's going to be minimal if you remove one of these variables. Okay, it's not a cover anymore. Okay, it's like the strongest possible cover. Okay, so when you look at these covers now, okay, so we have a particular constraint there. We take a cover. So I'm going to show you an inequality which is valid. Okay, and so what we do is basically that's what I told you before, right? If we select all these variables at the same time, right, we're going to violate the constraint. So the constraint is basically saying at least one of them has to be 0, or the sum of all these guys has to be smaller than the size of this cover minus 1. You can't select all the variables. This is what this is telling you. You can't select all the variables. So in a sense, the sum of them has to be smaller than the size of the set minus 1, or at least one of them has to be 0. You can think about it both ways, and that's what we're going to do anyway. Okay, so these are the cover cuts. Okay, so if you look at these constraints here, this is a big constraint, right? So 7 variables with coefficient, 11, 6, 6, 5, 5, 4, 1. Okay, and that has to be smaller. The sum of these things have to be smaller. These variables have to be smaller than 19. Okay, can we find a cover cut? Okay, so that's going to be easy, right? So we take in this particular case the coefficients by, this is decreasing order. I made it easy for you, right? So this is 11, 6, 6, so that's already 23, right? So this is greater than 19, so this is a cover, okay? And because of that, you know that x1 plus x2 plus x3 has to be smaller or equal to 2. You can only select 2 of these variables to have a feasible solution. Okay, now let's look at x4, x5, x6, x3, x4, x5, and x6. Okay, if you sum all these things together, once again, you get 20. This is greater than 19. So this is also a cover, and this is the cover inequality that results from them. Okay, the sum of these 4 variables has to be smaller or equal to 3. Okay, so this is essentially, so you start from an inequality like this with big coefficient, and then you have a very simple cover inequality there, which is limiting the set of the sum of a subset of the variables. Okay, these are cover cuts. Okay, now you can extend, you can make them stronger, and the key idea is that if you have a cover cut, you can extend it by taking other variables whose coefficients are greater than all the coefficients of the cut. Okay, so this is what this formula is explaining. Okay, so now instead of having the sum over the cut, you have this extended set. Okay, you extend the cut C. Okay, and what you do is you take obviously C, but also all the other variables whose coefficient is greater than all the coefficients of C. Okay, so by definition that these variables, okay, so they will essentially the cut will be stronger. Let me show you an example. It's easier on an example. So you see essentially the cover cut that we have seen. We had the cut which is x4, x3, x4, x5, and x6 has to be smaller or equal to 3. You see that the coefficient of x1 and x2 are greater than all these coefficients. So you make the cut stronger by adding x1 and x2 on this. If the coefficient would be weaker, it would not be as strong. But here the coefficients are always at least as strong as the coefficients of the other ones. Okay, so that's the stronger cover. Okay, now this is the idea of branch and cut. Okay, so the branch and cut consists of modeling first the problem as a MIP. Now you have a MIP. Okay, so you can use the linear relaxation. If the linear relaxation in step 2 is giving you an integral solution, the solution is integer, you are done. Okay, finished. Okay, so you have an optimal solution. Otherwise, what you do is you basically find a polyhedral cut, okay, which cuts the optimal solution to the linear relaxation. That's the key step, okay? And obviously, you would like to have a facet if it's possible. And so if you find such a beautiful thing, right? So what you're going to do is go back to step 2, you solve the linear relaxation. It's stronger. Why is it stronger? Because you cut the optimal solution to the linear relaxation, and you iterate this step. Okay, and at some point you can't find any of these cuts anymore, okay, because you have found all of them, or it's too tough to actually find them, okay. And then what you do is you branch, and then you can repeat these steps, or you can at some point decide that it's not even worthwhile generating more cuts, okay. So, but this is the basic framework for branch and cut, okay. Now, the key point here, okay, is that we have to generate these polyhedral cuts that are going to remove the value of the optimal solution, okay, of the linear relaxation. Okay, so this is what we need to do. Okay, so we are not going to do what I did in the previous lecture, which is just listing all the possible cuts we could find. Okay, what we want to do is that at some point we look at this linear relaxation and we say, wow, okay, so I want to cut it. Okay, so to give you an analogy, you have to think about feeding babies, right? So there are two types of parents, right? So when you have a new kid, okay? So what you do, you have the parents that read the books and do everything by the rule, okay? It's written in the book that this kid has to basically be eating every 3 hours. So this poor kid is sleeping, but 3 hours is gone. So they wake up this kid and feed the kid, right? So and then try to put the kid to sleep, and that never works, of course. Okay. So these are the essentially generating all the cuts. Okay. And then they are the cool parents, right? So I'm not saying that this is better or worse, right? So, but they are the parents that are saying this kid is, sleeping, beautifully. I'm going to let this kid sleep, and then when the kids, wake up and yell, you don't know why, but essentially you basically feed the kid at that point. That's demand feeding. That's what we are doing. We are generating these cuts by demand. Okay, so this is what we're going to do, and that's called the separation problem, okay? So what you know is that you have this optimal solution, okay, to the linear relaxation, and what you want to do is you want to look at a particular cut of a particular class of cut that's going to remove the optimal solution to this linear relaxation, okay? So this is what we do for cover cut, okay? So we have this optimal solution to the linear relaxation, and we are wondering, can I find a cover cut that's going to remove this optimal solution of the linear relaxation, okay? So we know that the cover inequality, okay? So this is this B right here, saying that this subset of variables, if I sum them to 1, okay? So if I sum them, they can't all be 1, so they have to sum, their sum should be smaller or equal to the cardinality of the cover minus 1. So that can be rewritten in saying, oh, at least one of them may be 0. So you do minus the variable. Okay, so that's going to be 1 if the variable is 0, or 0 if the variable is 1. Okay, and so you're basically saying here is that the number of variables which are 0 has to be greater than 1. Okay, and so essentially finding a cover cut, okay, will require two conditions. Okay. So we want obviously to find a cover. That's the second conditions that you have. Okay, so when you take the sum of these, when you take the sum of the elements in C, okay, the elements in the cover, that is to be greater than, the sum of the coefficient is to be greater than the right-hand side of the constraint. Okay, and then we want to be sure, we want to have the property that in the linear relaxation, these guys are smaller or equal to 1. So they are basically violating the cover cut. Okay, so essentially what we want to find is a cover cut that is violated by the linear relaxation, okay, and is a cut, okay, is a cover cut, okay. So we want these two properties. If we find that, essentially what we are doing is generating these cuts on demand, okay. So you say, oh, I have this linear relaxation, okay, I want to find a cover cut, and that cover cut is to violate this, it's to be violated. That's what you are trying to do, okay. So essentially, this is, we have two constraints here, okay? So we could view that as a feasibility problem, but we can also view that as an optimization problem because that's what linear programming does, right? So, or mixed integer programming does. And so what we do here is we minimize this expression, okay? That's the expression that we want to be smaller or equal to 1, smaller than 1. And then we have the definition of a cover cut there. So essentially what you do is you look for these variables zi, okay, zj in this particular case, okay? So you look at all of them. These are essentially the, all the variables, the indices of the variables inside the constraints. You want, to select a subset of them which violate the cuts and minimize this function, okay? And so now if the value of this function is smaller or equal to 1, you have a cover cut, okay? And all the elements which are equal to 1 are the cover, okay? So essentially if you solve this linear program, okay, this mixed integer program, okay, so you have a cover cut. You find a cover cut. Now you're going to tell me, wow. You guys are trying to solve mixed integer program and you want to solve another mixed integer program to solve that integer program and you want to do that repeatedly, what are you doing, okay? And so let me address that question in a moment, okay? So, but first let me give you an example, okay? So what you see here is a big constraint, so actually bigger than the other, the one that I've shown you before. The right-hand side is 178, and you see coefficient, ranging from 45 to 125. Okay. Now assume that the linear relaxation is giving you this optimal solution. Okay. So you see that the first one is 0, the second one is 0, the third one is 3/4, the fourth one is 1/2, and then it's 1 and 0. Okay. So how do you generate? Okay. So what is the MIP program that we have to solve to find a cover cut? So this is the MIP program actually solving the separation problem. Okay. You minimize Z1. Why Z1? Because essentially you take 1 minus the value in the linear relaxation, which is 0, okay? So that's why you have Z1. Then you have Z2 for the same reason. Then you have 1/4 of Z3, okay? Why? Because you see essentially 3/4 of the, 3/4 here. So 1 minus 3/4 is 1/4. And that's how you get this objective function. That's essentially what we saw on the previous slide. And then, of course, you have to have a cover cut, okay? And so you want basically that the choice of the value, the 0, 1 values for the z's is going to basically be greater than 178 when multiplied by the coefficients. Okay, so essentially this is the MIP program that we have to solve for finding this cut. Okay, so this is the separation problem. Okay, if we find a solution to this, we'll be separating. We'll find a cut which essentially separates the solution to the linear relaxation and the convex hull. Okay, so this is, I told you this is this beautiful mixed integer program. And so the question that I'm asking you is, does it remind you of something? Okay, so it's minimizing a linear sum of 0, 1 variables subject to some, the sum of these variables is to be greater than something. Okay, well, look, if I do a variable transformation, okay, rewrite the zg into 1 minus yg, okay, what do I get? Well, this minimum is going to be a maximum, okay? So we're going to maximize a sum of variables, okay? And this inequality here, which is greater than, is going to turn into an inequality which is smaller than. It's going to be a sum of variables with coefficient smaller than something. So what we have there is a knapsack problem, okay? So it's like, we have closed the loop in a sense. So we started with the knapsack, and now we are generating this branch and cut using a knapsack algorithm here, okay? So this is essentially the way you can do branch and cut, okay? So you basically solve the linear relaxation, and then you have various class of cuts, and you say, ooh, can I generate a cut that's going to separate the optimal solution to the linear relaxation? And you solve this separation problem and find these cuts on demand, okay? So before we move to the TSP, which is going to be kind of, big notation, so I want to go into a little bit of history here, okay? And we're going to talk about the 7 bridges of Königsberg, okay? And so this is the city where Euler, the great mathematician Euler was living. And this is a very interesting city because it's going to have, as the title indicates, 7 bridges, right? So let's zoom. You see the river, in blue, okay? And you see all these bridges in red, I assume, okay? And so what Euler asked, I think this is what he was spending his free time doing, is that can I find a tour which would go, which would walk over every one of these 7 bridges exactly once? Okay? And so this is, for instance, a tour that you see here, okay? So which is basically going over, 5 of the bridges. Okay, we can go through 5 of them exactly one. Can we go to 7 exactly once? Okay? And so what Euler did is one of the founder, obviously, of graph theory, is basically represent that as in beautiful pictures, okay, right? And then he looked at that picture and said, this is really a graph, okay? So I can associate a node with every one of these land masses, okay? And now the edges between these vertices are going to be the bridges, okay? So you see that here, I have 2 bridges between these 2, land mass. Okay, and so the question was, can I have a tour, that visit every one of the edges exactly once? Okay, so an Euler look at this problem and say, no, I can prove that this is impossible. You don't have to try walking this thing forever. Okay, and one of the ways the way he actually proved that is by looking at every one of these vertices. Okay, and obviously when you walk from one vertex to another one, you go to a particular point and then you go to another one. So as soon as you enter a vertex, you have to leave it, right? So that basically means that if you go over all the bridges, okay, you have to make sure that the degree of every one of them has to be even. Otherwise, you will come and there would be no bridge to get out of it, right? And so he could prove that in this particular case, you could never walk exactly once on these 7 bridges because, all these vertices here at, an odd degree. Okay, so in a sense, he invented kind of these degree constraints, and they are going to be very useful for our next topic, which is the traveling salesman problem. Now, the traveling salesman problem can be seen as the dual kind of, well, it's not really dual from a mathematical sense, but it's basically the opposite of the Euler path, the Euler 2 problems. What we want to do here is to visit all the vertices exactly once, not the edges. Okay, and there is a big difference between the Euler 2 and the traveling salesman problem. One is easy to solve, the other one is very complicated to solve. Okay, so what we do in the TSP is that we want to find a tour which is visiting every one of these vertices exactly once. Okay, and so the first thing that we have to do now is to try to model this as a MIP, right? So when we want to do branch and cut, what you do is you model this thing as a MIP. Okay, so you have to choose the decision variable, the constraint, the objective function. Okay, now there are many models to do that, right? So and we're going to use one which is very, very good from a computational standpoint, but you'll see we're going to build it step by step. Okay, it's going to be kind of nice. Okay, so the decision variable here are going to be deciding whether an edge is part of the tour or not. So we're going to look at every edges, okay, and we will associate a decision variable, a binary decision variable, telling us whether that particular edge is part of an optimal tour or not. Okay, and so the constraints are going to be this degree constraint. We know that if we go to a vertex, we have to get out of the vertex. Okay, so and since we can visit the vertex exactly once. Okay, so it's not like it has to be even, it has to be exactly 2. You want to go to the vertex and you want to get out. Okay, so essentially if you look at the vertex, 2 of its adjacent edges, okay, exactly 2 of these adjacent edges have to be 1. Okay, so this is the first, so I'm going to kill you with notation now, but this is essentially the basic of the model, of the first MIP model. Okay, so I told you that I'm going to kill you with this notation, so I'm going to try to go slowly so that you can memorize everything, okay? But essentially the decision variables are going to be very easy. For every edge E, you have xc, which is a decision variable, which is 0 if you don't take the edges in non-optimal solution and 1 if you take it, okay? Now V is always going to be the set of vertices, E is always going to be the set of edges, okay? And then the 3 notation are important, okay? So the next 3 notation are important. So I'm going to use delta V, okay, as the set of edges which are adjacent to vertex V, okay? So I look at the vertex, and then I look at all the edges which has V as one of their endpoints, and that's delta V. Okay, so when you see delta V is the edges associated with V. Okay, so far so good? Okay, delta V, the edges adjacent to V. Now delta S for a set of vertices is a little bit more complicated. Okay, so it's the set of edges which has at least one of their endpoints inside, which has exactly one of their endpoints inside S. Okay, so essentially they are adjacent to the set S. You see a set S of vertices, and these are edges which have an edge between an element, a vertex of S, and an element which is not in S. Okay, so that's delta S. So delta S, delta V, the set of edges adjacent to V. Delta S, the set of edges adjacent to a set of vertices, which means at least one of them. Okay, and then we're going to give F gamma S, which is essentially the set of edges whose both endpoints are inside S. Okay, so this is like you look at the set of vertices and you look at the edges in between them. You don't go outside. Okay, so these are the only notation that we're going to use. Then we have another. We're going to say X and then a set of edges to denote the sum of the variables associated with every one of these edges. Okay, so when I say X of E1, E2, E3, and so on, that basically means the sum X for the first edge plus X for the second edge plus X for the last edges, and so on. Okay, so once we have this notation, this is how we can have a first MIP model for the TSP. Okay, so what we do is we minimize the length of the tour. Okay, so we take the cost of every edges and multiply by the binary variable telling you if you take the edges or not. Okay, so that's minimizing the cost. What you see over there are basically the flow conservation or the degree constraints, which are basically telling you that every time you go to a vertex, you have to get out. Okay, so and this is basically telling you that if you take the set of variable X, okay, and the set of adjacent the set of adjacent edge to the vertex V, okay, the sum of these variables is to be equal to 2. Okay, take the adjacent edge, take the sum of the Boolean variable associated to these edges. It has to be the 0, 1 variable. It has to be equal to 2. Okay, and then obviously the edges have to be 0, 1. Okay, so if we take a traveling salesman problem, we use that MIP formulation. This is one of the things that can happen to you. Okay, you're going to get a solution like that. Okay, so this is not obviously a tour. What you get is a bunch of subtours. Okay, tiny tours. Okay, so you have this one. Okay, so you have this one. You have this vertex. Going to that vertex, going to that vertex, and then going back there. Okay, so instead of going back to something else, it's basically going back to the first vertex of this subtour, and then you have another subtour, a third subtour, and so on. And obviously, this is very clever, right? So because you don't have to travel these long distances between these things. Okay. So that's terrible. We don't want that. So what we want to do is we want to look at a particular vertex like this, a particular subtour like this, and we want to say, ooh, can I remove the fact that this is a subtour? Okay, so if you look at that, these 3 vertices, and you see you ask yourself the questions that how many edges can actually be selected between these vertices. Okay, and obviously you can't have 3, otherwise you have a subtour. Okay, so the maximum number of edges here for n vertices is going to be n minus 1, right? So in this particular case, it's going to be 2. Okay, so and these are called the subtour constraints. Okay, and so what I'm showing you here is a formulation, and a better formulation, for the TSP, where we put these subtour constraints. Okay, so what we are basically telling you here is that if you take X and if you take a particular vertex, a particular set of vertex S, okay, and then you take all the edges, which are inside that set, okay, so that's gamma S. Remember, gamma S are all the edges which are between vertices of S. You know that the sum of these edges, the sum of the Boolean variable associated with these edges, has to be, smaller than the cardinality of S, the set of vertices, minus 1. Okay, so you have to get out of there. Okay, so that's what it is basically saying. You can have, S minus cardinality of S minus 1 edges, but you have to be able to exit. Okay, so that's what you have there. Okay, so these are called the subtour constraints. Okay, so you look at every subset and you place these particular constraints. Okay, now, but what is the issue with these subtour constraints? Well, once again, there are exponentially many of them. So you don't want to write them all down, right? Because that's going to be kind of long. Okay, so what you want to do is exactly what we did with the cover cuts. You want to generate them on demand. Many of them you will never generate. Why? Because you take something. If you do a tour of the U.S., you're never going to connect Orlando and Seattle, right? And then San Francisco. So generating a subtour for this thing is completely useless. The relaxation is never going to do that. Okay, so what you want to do is look at these subtour constraints and see which one are violated by the linear relaxation. Okay, so you want to generate them on demand. Okay, and to do that, you need a separation problem. Okay, so how do you do the separation problems? I'm going to give you the intuition. I won't go into the detail, but this is beautiful. Okay, so what we can re-express the constraint by saying that the set of the edges adjacent to us, between a set of variables has to be smaller than the cardinality of 1, the cardinality of the set minus 1, by saying that we have at least 2 edges that are coming to this set and going out. Okay, and this is what you see here. Okay, so what you see in this constraint there I took a set S, okay, and then I have delta S, which are the edges which are, at least one of the endpoint is outside S, okay, and exactly one of the endpoint is inside S. And so what I'm basically saying here is that the sum of the edges, which one of the endpoint is in S, the other one is outside, has to be greater or equal to 2, okay? Which means, oh, I have to get in and then I have to get out, okay? So that's what you can re-express it that way. And once you re-express it that way, the separation problems become a really nice combinatorial problems that can be solved in polynomial time. The key idea here is that you will build a graph, okay, with the same set of vertices, the same set of edges, okay, and the weight of the, and so for every one of these edges, you are going to assign the weight of the edges is going to be the value in the linear relaxation, okay. So you basically build, you have the same graph, but no, the edges get a weight, which is essentially the value of the decision variables of that edge inside the linear relaxation. And now what to find a subtour constraints, okay, that is violated, what you're going to do is try to find a min cut in that graph. So that means cutting the graph into 2 parts, okay, such that that of minimal size, okay, to minimize the number of edges between these 2 different subsets, okay. And if the weight of the cut is smaller or equal to 2, you have a problem, right? So you are basically violated the subtour constraints, okay. So you have isolated the subtour constraints between some of these vertices, and you can find the subtour constraints and state it inside the linear relaxation, okay. And finding some of these cuts, okay. So finding these cuts is polynomial time. The simplest algorithm would solve a bunch of max flow min cut problems and generate the cut by that. But there are better algorithms to do that actually in practice. Okay, so now you know how to separate these subtour constraints. So you can do this branch and bond where you start with the linear exchange, add them until you can't actually find any subtour constraint which is violated. Okay, does that mean that at that point you have a solution to the TSP? No, okay? So why? This is a solution, okay, which satisfies all the subtour constraints, all the degree constraints, okay? So you can't imagine how long I took to generate this, okay? But it violates some of the subtour constraints. Okay, it doesn't violate the subtour constraint, but it has a fractional solution. Okay, and there are actually cycles here. Okay, so what you see here, look at this particular cycle here. Okay, so all the values are 1/2. When you sum, okay, the sum is smaller or equal to 2. Okay, it's 1.5, it's smaller or equal to 2, which is fine. You are not violating any of the subtour constraints, but still you have a cycle and you have fractional values there. So what does that mean? That means that the convex hull of the TSP is not characterized by the subtour formulation that I've shown you. We need more of these cuts, okay? And so it's a whole industry to actually generate very good cuts for the TSP, okay? And there are some beautiful results in that space. And so I'm gonna give you one class, okay, which is very useful in practice, which are called the comp cut. Comp, combing, okay? And so the basic intuition here is that if you look at the tour and take a kind of a line, okay, and wonder how many of these edges you are intersecting, you're going to intersect an even number of them, okay? Whatever you do, it's always going to be an even number, okay? So now you can start reasoning about these crossings, and that's what comp cuts are doing. People in optimization are really creative in finding good names, okay? So what is a comp cut, okay? So this is something that has a handle and a bunch of teeth, okay? And then you have nodes, we have edges which are purely between elements of the handles, and then edges which are purely inside the teeth, okay? And then you have edges between the handle and the teeth, okay? And the key idea is that what the comp cuts are going to do is bond the number of edges that you can have inside purely inside the handle, purely inside the leaf, because that tells you also that you need a certain number of these things that are connecting the handle and the teeth. Okay, and so this is an example of this is a cut. Okay, there are many classes of these comp cuts, but this is a general comp cut. Okay, it's basically looking at limiting the variables which are basically the edges inside the handle and inside the teeth. That's what you see here on the right-hand side. So this is the number of edges inside the handle, the number of edges inside the teeth, and that's basically bounded by the size of the handle, the size of the teeth minus these things, which are basically expressing the fact that you have to connect the handle and the teeth. Okay, so in this particular case, if you compute this expression on this example, this is going to give you the value 7. Just do it for yourself. It's very interesting. Okay, and so 7 here is very interesting because what? When you look at the edges inside the angle, there are 6 of them. There are also an edge inside that teeth. That's also 7. So this constraint is actually tight. Okay, so that means that you can't select more edges. If you select these edges, you can't select more edges inside the handle. So for instance, you could not select an edge going from here to there. Okay, so that would not be good. Okay, so essentially these comp cuts are basically, more interesting, facets of the polyhedral cuts of the traveling salesman problem. Now, I want to a little bit give you the perspective on how strong the relaxation becomes when you put these things. When you put the Subtour elimination on the set of benchmark of the TSP lip, which has some really nice problems, which are not that easy, but some of them are really large. Okay, so you come within 2% of the optimality gap. So the distance between the optimal solution and the linear relaxation is 2%. So if you do the subtours and the comps, okay, so you get to 0.5% of the optimality, which is really, really good. Okay, for larger instances, you will need more cut. There are things like local cuts and things like this that will be needed to actually prove optimality or really, really, really large TSP. Okay, so if you want to know more about this, there is a beautiful book by Bill Cook, just on the traveling salesman problem. Okay, and it's a fantastic book because it basically gives you history and all kinds of things. It's like addressing people who don't necessarily have a background in optimization, but also giving you some of the technical details. So it's a really nice balance. So if you want to know more, read that book. Okay, so this is basically covering branch and cut. Okay, so what we saw, branch and cut in summary. Okay, so what you do is you solve the linear relaxation based on a MIP, and then you generate on demand, okay, all these constraints to cut the optimal solution to the linear relaxation, and then strengthen the relaxation. When you stack, you're going to branch, and you can repeat that process. Thank you.